PowerPoint by clicking the 2016 March 7 Ferris Wheel and Test Review link, and then you click Browse to, you can browse to that PowerPoint. So let's get started. I hope you have checked your email and also watch all the news items. Look at the news item to check the updates as always. Log into your Georgia Virtual School emails every day. There might be some extra credit there. There will also be one extra credit at the end of this PowerPoint. Alright, just a quick review. Not sure how much knowledge you have about unit circle. Unit circle is a circle with one on each axis. Okay, it's only one unit, and it's like any xy points. The unit circle could be, it has 2 pi and pi, and also there are more explanation here that we are going to look at. If you want, you can click on this link, and we are going to look at it on a web page together. So here's a unit circle. The unit circle is a circle with a radius of 1. Being so simple, it is a great way to learn and talk about lengths and angles. It's used in trigonometry a lot, and the circle is put on a graph where the x and y axis cross. So it starts with the origins. So we get this neat arrangement here. Because the radius is 1, we can directly measure the sine and cosine and tangent. Okay. We will also have a quick review of sine, cosine, tangent from here in this office hour recording. So I will leave this. Unit circle is not a main focus for this content. However, I just want to give you a quick overview what it is. And I have posted some tutorial videos. And here, remember unit circle. Okay, please check out our user links here. There are new tutorial section and also helpful websites. If you have any question regarding Brightspace, you should click on Brightspace, an online graphing calculator, and a student handbook are here. So please check out the news item every day. So now we will move on to the next part. The 3 basic trigonometry ratios, which is sine, cosine, and tangent. Sine of theta, which is the angle, okay, is a ratio. Sine of theta is a ratio of the opposite side of the right triangle to the hypotenuse. And cosine of the angle referred to is the adjacent side, right next to it, to the hypotenuse of the right triangle. Tangent of the theta is the opposite side over adjacent. So in short, we have this short saying so, ka, toa, to help you to remember the ratio of these 3 trigonometric ratios. today we are going to use the cosine theta to help us to solve our Ferris wheels questions. These questions is taken from the content that is provided in this course for you. And I only want to break it down because by looking at the content, I consider some of the students might not understand it. And I'm hoping breaking it down here during this session will help more students to understand it. And at any time after watching these videos, you still don't understand, please let me know. I will try my best to explain to you. So let's read. If you haven't read the content, you should always go to the content and read the content. And this is from the content. On February 11, 2008, Singapore opened a new observation wheel called the Singapore Flyer. At the time its opening, this giant Ferris wheel was the tallest in the world. The Singapore Flyer consists of an observation wheel with a diameter of 150 meters atop a boarding terminal, giving the structure an overall height of 165 meters. Only the platform itself is 15 meters. 15 meters is tall. Okay. 28 air-conditioned capsules rotate on the outside of the wheel to provide unobstructed views of the city. The wheel rotates at a constant rate of 26 centimeters per second. This is slow enough that the wheel does not need to stop for loading and unloading unless there are special passenger needs. Describe how they will calculate the capsule height above the ground. Draw and label your diagram. An accurate diagram of a wheel showing dimension given above. Okay, so we know the total height is 165. This is total height. And out of this height, 15 of them right here, this is a boarding terminal. And the diameter is right here. This is the diameter of the Ferris wheel, which is 150 meters. Okay, so now we are going to describe how they will calculate the capsule height. We want to calculate, at any minute, how tall is each capsule height from the ground. That's our goal of this activity. Alright, Ferris wheel content. So continue. At time 0, the capsule is in a boarding terminal. How high above the ground is the capsule at this moment? So, if it's at a boarding terminal is right here. So how high it is from the ground? It's pretty simple. It's 160 meters, the total height. Subtract the diameter, that give you 50 meters. At 1 minute, how far has the capsule traveled around the circumference of the wheel? Given the information, let's see. So what it means is we want to calculate, let me see. Let's change to red. Okay, if after 1 minute, let's say after 1 minute the capsule got here, right? We want to know how far is it from the ground. We want to know this. Okay? And we are going to be able to figure it out. Let's say this is a capsule using a right triangle that I'm going to show you the next page. Okay. But since the wheels rotate at a constant rate 20 centimeters per second, given a problem, and there are 60 seconds in a minute, we know that at each minute he has traveled 15.6 meters. So this is how we calculate. Okay, because since we want to calculate 1 minute, right? How far the capsule has traveled in 1 minute. We want to know, like, okay, how tall it is. So we want to know how far it had traveled around the circumference. Okay, and we know that the speed is 26 centimeters per second. So using that information multiplied by 60 seconds, we know it has traveled 1,560 centimeters. Or when you centimeter to meter, 1 meter is equal to 100 centimeter. Okay, so given that 1,560 centimeter become 15.6 meters. Okay, that's only around the circumference. That's not the height of the capsule from the ground. What we had just calculated is only around the circumference right here. Okay, but we actually need to find this height right here. So let's look at the picture. What is the height of the capsule from the ground given after a given minute? So this is further illustrate what we're talking about. Here's the ground, and this is the height of the capsule from the ground, and we want to look for this. Alright, so here's our strategies. Okay, notice the right triangle you can draw within your diagram. Okay, let's say this is a capsule right here, and connect where the capsule is to the radius, and then this right here, this line right here is the hypotenuse of the right triangle. Okay, this line right here is the hypotenuse of the right triangle, and that is also the radius of the circle. Okay, so if this is 75, meaning this is also 75 right here, this length right here. Okay, and where's the right triangle? It's right here. The right triangle is right here. Okay, and the theta, the angle that we're looking at, which is the angle, the center angle where the capsule is traveling, we want to know how far has it traveled. It has traveled this much. This is the angle that we're looking at right here. Okay, and we call it theta. First, we need the angle of the rotation. We need to figure out what the angle is, and then we will calculate the total time it takes to rotate one circle. Then you use it to calculate the angle. Okay. Second, we will calculate the vertical leg of the right triangle A. We calculate this side right here. Okay. We calculate this side right here. Third, to get the total height, we will subtract A from the radius and then add it to the height of the platform. So since we know this whole thing is the radius, okay, and after we calculate A, we will subtract it from the radius to get this part right here, this black part, and then we add it to the platform 15 to get the total height right here. Okay. If the angle of rotation is greater than 90 degrees, then you will need to add it to the angle of rotation. Okay. View in the table below showing the height. These are all from the content. Showing the height of a single capsule changing as it rotates counterclockwise from the boarding terminal around the wheels. To do this, first calculate the circumference of the wheel. Okay, so the circumference formula is 2 pi r, and we know the radius is 75 because it's half of 150. So you enter in your calculator, you should get 471.24 meters or 47,124 centimeters. Okay. The reason we need a centimeters because the speed of the capsule was given in centimeter per second. Okay, so we want to know how many minutes does it take a capsule to make one complete revolution around the wheel, round to the nearest minute. Explain the process. So the wheel is traveling at 26 centimeters per second, and the distance it must travel is 47,124 centimeters. So using our most basic formula, distance equal to rate times time, the rate that was given is 26 centimeters per second. You put it right here, and the distance is the whole circumference because that's what we calculated. And because the distance equal to rate times time, now to get the time, we use distance divided by the rate. Okay, so distance divided by the rate, distance divided by rate. And you get 1,812 equal to the time. And that's in second. The reason it's in second because the rate is in second. So there are 60 seconds in a minute. You convert it into minutes, you get approximately 30 minutes. Okay? So the reason we convert it back to minute because the question was asked in minute. So here's the first step. We are getting the angle of rotation. Okay, before completing the table, explain how the angle values provided in the tables are correct. This is what's stated in the content. Okay, if a wheel takes 30 minutes to make one complete revolution, okay, so if you start right here, for you to go back down to the ground, it takes 30 minutes. Then 1/30 of the circumference is passed through each minute. Therefore, a single capsule that had rotated 1/30 of 360 of the circle, or 12 degree. Okay, so this is 360 divided by 30 minutes. You get 12 degree per minute. Okay, that is the central angle. That is the central angle that we were looking at. Just now we were looking at this. Let's say this is capsule after 1 minute. This is angle right here that we're looking at, right? Imagine there's a right triangle here, and there's a right central angle is 12 degree. So right here, that's the angle right here that we're talking about. Okay. Now, so here I pulled a table out from the content. So this is from the content. The first inscribed angle that models the situation after 1 minute is shown. Use additional diagrams and inscribe right triangles to determine more values of the total height as the given capsule continues to rotate through one complete revolution. Use trigonometry to calculate the corresponding values of A and complete the table, finding the height of the capsule at a various interval of time. So, meaning complete the table, okay? The first minute, we know the angle is 12 degree. So if the angle is 12 degree, How are we using cosine to calculate the vertical leg of the triangle? We know cosine theta is equal to adjacent over hypotenuse. And here's my my triangle. Let's draw. Right here, my theta, okay? Okay. Okay. So this is theta, my opposite is right here. This is my opposite. This is my adjacent. This is my hypotenuse. And the length that we want to calculate is the adjacent side. Okay. So since we know using the formula, okay, cosine of the 12 degrees, okay, here's the 12 degrees, is equal to adjacent, which is the adjacent side right here, over the hypotenuse, which is 75. Okay, the hypotenuse is the radius of the circle, which is 75. So, using your cross multiplied, okay, so A is equal to 75 times cos 12 degrees. You use your calculator, find the you should have a scientific calculator should have a cos. So cosine 12 degree multiplied by 75. Make sure your calculator is set to degree and not radian. Okay, then you should get your answer. Okay, as a 73.36. .36 the answer here. Okay. So using that, we are going to move on to calculate the total height of the capsule M. And we know that we just calculate 73.36 for this height right here, right? We just calculated that. And the platform height is 15 meters. So now we need to figure out this pink height right here. Okay. So to get to the pink height, I use the distance, which is the radius, subtract my 76.36. So I got this pink height, and then I add it to the 15, I get my total height, which is what label here, which is how tall is my capsule from the ground. Okay, so diameter subtract A plus platform height, then you will get your total height from the ground. 16.64. This is just the first angle. For first minute, your capsule is 16.64 meter from the ground. All right. So now, if to fill out the rest of the number, you know the first minute is 12 degrees, the second minute will be 24 degrees, which is 2 times of 12. And the third minute will be 36 degrees. And you just keep multiply 12 until you get to 360 degrees, which means you came back down to the ground. And then the same way to get the rest is cosine of 24 degrees and then you use same process. You get 75. I just type. Subtract your answer that you got. Okay, then plus 15. And using this process, you should be able to get all the answer on the table that is already shown in the content. All right. So next part of the review or extension of the explanation that I'm going to show is a quick intro or review of sine transformations. You need this information to help you to do well in your test and quiz. The sine function can be transformed, meaning it could make it big or small, taller, shorter, or move left or right by changing the parameters of the functions. There are 4 parameters that you can change. The first parameter is the number. It's called like the coefficient of the sine function, a number in front of the sine functions. Okay, that number stretches or squeezes the graph up and down. It stretches the graph up and down if a is greater than 1, any number greater than 1. It squeezes the graph if a is between the number 0 and 1, let's say 0.5, any number between 0 and 1. It flips the graph top for bottom and squeeze it. Two things, it flip the graph because if a is between 0 and -1, because it's a negative number, and because it's a number between 0 and 1, and it's a negative. So it flipped it and it squeezed it too. It flipped the graph top for bottom and stretched it. Okay, if a is less than -1. Okay, so it's pretty easy to remember. If the number that is larger than 1, it stretches it. If it's a negative number, it flips it. Okay, B is a number in front of the x, okay, or the number in front of the domain. If the domain is in a radian, which is in pi or 2 pi or pi over 3, then that is the x that we're talking about. That is the input. Okay? The number in front of the x stretches or squeezes the graph left and right. Okay? So if b is greater than 1, it stretches the graph. If b is between 0 and 1, it flips the graph left for right and stretches it. If b is between 0 and -1, flips the graph left for right. It's like mirror, rotate around the y-axis, and squeezes it if b is less than -1. And C moves the graph left and right, D moves the graph up and down. And we are going to look at it on a decimal graphing calculator. Hey, why is it not clickable? Let me try it again. Oh, it does work. All right. So here's A, okay? Here's a decimal graph, okay? This is a sine function that I just put in, and I put in a different parameter for us to play with. Okay, if I move my A to see, if I move my A is usually 1. Okay, 1 is a normal number. You cannot have A 0. Then it will just go flat. Usually A is 1, and that's my normal sine function. Okay, if my A is larger than 1, got longer and longer, it stretches it. Right? If my A is less than 1, now it make it flatter and flatter. Right? If my A is negative, the A is positive. If my A is negative, see, it kind of flips it. Okay. So this is the effect of A. B, left and right, okay? See, it's pull left and right. And C moving in left or right. It doesn't stretch or squeeze, but it just moves the graph. Now remember, C is usually 0, and because the formula has minus, so when you have minus positive number, it's move the graph to the left. Minus negative number, the graph is moved to the right. Okay. D moving up and down. All right. I hope this help with this understanding of sine transformation. And cosine function also transform, but cosine function is not a focus for this content. However, it's the knowledge that you might want to know. And here's the notes. You can take notes and keep it for yourself to use later. All right. Here's another thing that's very important for this unit. What is a period? Because we're talking about periodic function. Okay, the period is a horizontal distance between two maximum values or two minimum values. To increase the period, there would have to be longer time between two maximum values. So, you might come across question, how do I increase the period, increase the value of periods? So you will say, okay, I'll do this slower, something that's happened over a longer period of time will have a bigger period. This means it needs to take more time for a wheel to move from the top all the way around to the top again, from the top all the way around to the top again. Okay. In other words, you need to slow the rate of the Ferris wheel or slow the rate of your bicycle wheels. or anything that can be modeled by periodic functions. Anything that go and come back, go and come back, the wave, go and come back, go and come back. Anything else, the clock. Okay, periodic functions. Periodic functions are functions that repeat over and over, or cycle in a specific period. They are also known as cyclical functions. Sine and cosine functions are the most common periodic functions. In this topic, we're looking at sine and cosine functions as a periodic functions. Circle is not. Okay, here's some example. Any form of sine and cosine function are periodic functions. Examples, if I have changed any parameter of the sine and cosine, or I added stuff around the sine and cosine, they are still periodic